Oh, Chris Crosby from OpenTopography, primary investigator and head of the project management there. We're going to talk about statewide change, topo change at a statewide scale. UNAVCO, did I put the emphasis on the right syllable? All right, very good. Well, thanks, Chris.
Okay, thanks everybody. So like most of you, this is my first business meeting in what seems like forever. So it's cool to be here. It also seems a little surreal and weird. And so I'm going to talk today about OpenTopography, which is a project that I've been working on for 12 plus years. It's funded by the US National Science Foundation as a collaboration between the San Diego Supercomputer Center, which is a facility at University of California, San Diego, Arizona State University, and UNAVCO, which is where I work, which is in Boulder, Colorado, which is an organization primarily supported by the National Science Foundation and NSF and NASA. Hopefully everybody can see the screen okay. We got pop-ups, but that shouldn't be too big a problem. Let's see. So one of the things that I heard a lot of during the roll call was discussion about lidar and about these statewide lidar collections. And so what I'm going to talk about is OpenTopography as a platform for distribution of those kinds of data sets, but also sort of looking ahead to what we can start doing when we have really large scale, statewide or larger scale lidar data collections. And I'm going to talk about what happens when you just compute the topographic change of the state of Indiana at 1 meter resolution. And we've done this. I'm going to show you what it looks like. But before I do that, I'm going to talk a little bit about OpenTopography as a platform. I had a colleague who presented at NISJIC in Snowbird, which I guess was a couple of years ago now, and talked about OpenTopography. So some of you may be familiar with OpenTop, but you may have seen it out there otherwise. And so let's go through this. Here we go. So OpenTopography was built with a very academic focus. We get funding from the National Science Foundation to support earth science research and also education. But it turns out that the platform, which is built to manage point cloud data, as well as raster topographic products like DEMs and DTMs, DSMs, ortho imagery, is really actually useful on a much larger scale, right? So we built it to help earthquake scientists study the San Andreas Fault or study volcanoes or study landslides. But the platform, which allows users to access data through a web interface, is really useful for when to start thinking about what do I do when I have a state's worth of data or I have the whole country. And so OpenTopography is this platform. So this advancing thing doesn't quite work. Come on. Emily, can you hit the next button for me? Doesn't seem to want to go. You just hit the space bar or the arrow key. There we go. So OpenTopography is a platform for hosting data sets. We put them on a server at the San Diego Supercomputer Center and provide tools to access and distribute the data. We've also built direct access to USGS's whole 3DEP catalog now, which is something like 30 trillion LiDAR points across the United States. Whatever it is now, 65, 70, 80% of the United States land area has been collected by 3DEP. We've done a fair amount of work with education and training. So running lots of short courses and workshops and teaching people how to work with high resolution topographic data. I'm not going to talk about that at all today, but I'm interested to talk with you if that's something that people are interested in, which is just training around these data sets. And we've worked, again, our primary funding comes from the National Science Foundation, but we've really worked with partners from all kinds of different agencies. Our biggest partner right now is Land Information New Zealand. I'll talk about that more now, but they're using OpenTopography to distribute their nationwide LiDAR data set. So this is essentially the 3DEP program for New Zealand. One of the things that OpenTopography has done ever since day one is really emphasize the idea of data access co-located with processing tools. So we put the data inside our data system, and then we park on-demand computational tools adjacent to the data. So instead of just delivering people LAS files off of a file server like an FTP, we provide a suite of tools for people to actually derive products and visualizations from those point cloud data sets. So this is really powerful. That means that your end user doesn't necessarily need to know a bunch of geospatial software. They don't need to figure out what to do with dozens of point cloud files that might get downloaded. They get the product they want, which might be contour lines derived from that topography, or that might be a KMZ file with a hillshade in it that they can look at. So this is what we've been really trying to do, is abstract the access and the processing from the end user's interests, what they really want. We also provide APIs and bulk download via cloud optimized GeoTIFFs and all kinds of other sort of power user tools as well. But the simplest thing is just co-location of data and processing through a web browser. This is just a quick summary of the tools that currently live inside of OpenTopography. So there's a database of topographic data, and then there are tools for accessing point clouds and doing basic filtering on those point clouds, as well as kind of clip and ship subsetting of raster data. Then once you access the data, there's a whole bunch of tools that allow you to process those data into sort of standard derivatives. So this is rasters, at a user-defined resolution. So I want a 1 meter DTM derived from a point cloud data set. I want a canopy height model, the heights of the trees in the landscape. I want contour lines. I want visualization of that data, either in a raster space or a point cloud space. All of this is happening on demand through our tools. The other thing that we've really spent a lot of time on recently is topographic differencing. So this is when you start having overlapping data sets, what do you do with them? And what kinds of interesting things can we do? So we've got tools for doing change sort of in the vertical direction. So this is basically like simple raster math. How's the landscape changing in the Z direction, but also really sophisticated tools for doing 3D change detection. And I'll talk a little bit more about these because this is the basis for what I want to show you later. We've also done some work on hydrologic routing. So basically being able to route water over landscapes on demand. This is using the open source Tau DEM toolkit, which we've got running on a high performance computing machine right now. So this is kind of the suite of services that exist inside of OpenTopography today. Very quickly, it's a standard web GUI kind of interface, right? So there's a map, we search for data, you make a selection on the map, the system comes back and says, here are all the data sets within your bounding box. Some of those data sets are data that we're hosting in San Diego on our machines. And those tend to be more academically oriented data sets. But now we have 3DEP. So there's a tab there that says USGS 3DEP. And there's all the data sets within 3DEP are accessed dynamically. And every time the USGS publishes a new data set into Amazon's bucket, it appears in our system. Basically, we sync weekly. We've got global data sets like SRTM and other kinds of data sets that you might also be interested in. But the LiDAR and the high resolution topos are sort of the core of our services. Each page has a sort of set of branding associated with it. So this is, for example, a Utah state acquisition along the Wasatch Front. We have logos, we have different products, we have descriptions. Every data set has a digital object identifier. So if you want to be able to cite it or a persistent identifier, that's inside of our system. And then there's just a bunch of processing. So essentially OpenTopography is a discover data and then parameterize a workflow and say go, and it runs on our services in San Diego. And at the end, you get an email back after tens to hundreds of seconds that says your job is done and here are the things you can download. So it's a very simple way to allow a user to iterate and explore data without having to do anything locally on their machine. We're doing all the compute, all the product generation for them. Landing pages that have browse images and things like that. We also do point cloud-based visualization. So this is the Utah State Capitol in Salt Lake City inside a web browser visualization. So again, this is point cloud visualization through a web browser. This is using the Potree system, which is an open source tool that some of you may be familiar with. Really nice, doesn't require you to run any proprietary software or anything locally, but you can play with the data and explore it. So there's that. So as I said, we've built this system again primarily for academic users, but we've had this growing kind of momentum around leveraging OpenTopography for other types of data sets collected outside of that academic domain. That's kind of why I'm here today, is to talk to you as people who are collecting tons of this kind of data and potentially are looking for solutions to make it easier for your end users, your stakeholders to access. So we've been working with Land Information New Zealand. This is the National Mapping Agency based in Wellington. We've got 44 individual LiDAR data sets. You can think of these as each like a 3DEP collect or a 3DEP polygon. They're all flown to a very standard specification, much like the 3DEP process. 61,000 square kilometers of LiDAR, and they're in the process over the next 5 years of essentially flying the whole country, and all that data is going to end up in OpenTopography when it's done. And so this is a really cool and exciting opportunity for us, but it's also, I think, been pretty fruitful because it's demonstrated that these data sets become much more valuable. The return on investment in the considerable amount of money it costs to collect these airborne LiDAR data is greater when you make the data easy to use. So that's like one of the take-home messages here. We also have the 2011 to 2013 Indiana statewide LiDAR data collection. This was something that Phil Worrell helped to make possible. Phil came to us and said, hey, we're flying the whole state of Indiana. We want to make the data easy to use, but we don't really have a great way to distribute it. Can we just stick it in OpenTopography? And so we've done this, and it's been relatively successful. Something like 5,500 unique users have accessed this data, running 41,000 data access jobs. So that's like pretty significant utilization. This is downtown Indianapolis inside that same web browser visualization tool. Phil, basically, this was just a quote from Phil on this GIS Addressed podcast from a couple of years ago, just talking about this point, which is when you provide tools and pathways for people to access the data, people find it easier to use and they do interesting things with it. So like you're deriving more return on investment, you're making your stakeholders happier because your average engineering company or something can go and easily access the products they want, which might be a set of contour lines in DXF format, right? They don't want point clouds. And so that's really the power of OpenTopography. So that's sort of the transition from what was OpenTopography, where does it come from, to talking about this differencing exercise. So a couple of years ago now, the USGS, in partnership with Howard Butler, who's the guy who's built some tools like the point data abstraction library and some other open source tools, basically took the whole USGS 3.0 point cloud data set, published it into this format called Entwine, and dumped it all into an Amazon public data set. So there's something like 30 trillion points in this bucket. It's increasing every week. The USGS publishes more data roughly. And the cool thing is this is open access. And so what we did is we came along and said, well, this is really cool. And we can apply our OpenTopography tools to the data in the bucket. And so we just wrote a bunch of software that reaches into this thing. So we go out to the US West Amazon bucket and we clip out the data, and then we pipe it through our processing stream in San Diego. And so as of today, there's 31 trillion LiDAR points. It's 5.8 million square kilometers. Sorry, we think in kilometers. 1,588 unique data sets. Everything in green on this map is inside that Amazon bucket right now. And so depending on what state you represent, you can see that your data is in there. But it's relatively hard for the average person to get at, right? Because it's in this weird Entwine point tile format. You've got to write some software. You've got to, I think QGIS can now consume EPT format, but in general, it's a relatively hard thing for people to access. And so what we've done is we've just built this pathway. The other thing we just did, which we just released, is that actually the USGS is now also publishing the 3-depth raster data set. So this is the 1 meter DEM data, the 10 meter DEM data, and the 30 meter DEM data into a similar place. And so now we're actually able to deliver those data as well. So the red here is the raster derivatives, the 1 meters that are derived from those LiDAR 3-depth collects. So that's all inside of OpenTopography as well. And this is a really cool approach because it means we don't actually have to hold all the data on our servers. We're just reaching out into resources that are sitting in these Amazon cloud-based buckets out there. So this is really powerful because it enables us to code new interfaces. It would mean that other people can come along and do the same thing, right? So we're just one of many people probably who are utilizing that resource. Oops, let's go back. So moving on to topographic differencing. So the question becomes, well, this is really cool. So now we've got these large scale LiDAR collections like the 3-depth program, but not exclusively the 3-depth program, right? There are other states and other entities out there that are collecting these kinds of data that aren't inside 3-depth. So we can start looking at them, like we can start doing multi-temporal comparisons of data sets and just like thinking about how we can monitor change. And some of that change is natural, it's natural hazards, it's climate related. Some of it's anthropogenic, it's development and land use change. Some of the things we see are frankly about the quality of the data and errors and artifacts and other weirdness that are in these data sets. And so I'll show you some examples of this. As I said earlier, there's two types of differencing. There's vertical, which is just like change in the Z direction, vertical only. And then there's this 3D differencing, which works really well for things like earthquakes, where the land deforms, or landslides, where the landscape is translating. I'm not going to talk about 3D differencing because that's a little more sophisticated and actually is very specialized, but vertical is pretty common, right? Lots of things are changing in the up and down direction. So here's an example of what this looks like. Get familiar with these reds and blue maps because I'm going to show you a bunch of them here. But essentially, this is an example from White Sands, New Mexico. 2 airborne LiDAR data sets collected roughly 1 year apart, 2009, 2010. This is a very active landscape. The dunes are blowing to the northeast, as you may be able to tell. The color bar is red is erosion, so landscape going down. Blue is deposition. So you can see these sand dunes are marching northeast. There's sands being picked up from the southwest side, I mean deposited on the northeast side of the dune. So this is a very kind of clear signal of dynamic landscape change imaged in less than 1 year. Right? So what we basically do here is we go and we grab these point cloud data sets and we start with the point clouds. We don't start with the pre-computed rasters because those rasters aren't necessarily aligned to the same grid. So to do this right, you've got to line the raster, the DMs or the DTMs up on the same axis. So we start with the point cloud data, we create a raster, and then we subtract those rasters and you get a difference, right? Red is down, blue is up. And this is a very simple GIS operation, right? But we're doing it at the scale of the whole state based on cloud-based resources. We're scaling up this exercise to be something bigger than what you're going to do on a workstation in your own office. So the question is, why Indiana? Like, the answer is A, because we had worked with Phil and the folks from Indiana to put the earlier data set into OpenTopography. It's also one of the first states that has good quality wall-to-wall multi-temporal lidar collects, and so it's opportunistic in that way. This will become possible more so in the future, and I'll show you what that looks like potentially and where we can start thinking about this. But it's 36,000 square miles of data, and so you're not going to do this manually. So we've actually coded this all up as one big scripted process that runs, goes out, gets the data from the cloud, regrids it, computes the difference, writes out a bunch of products. We're doing this on the DTMs, basically bare earth. We're doing on the surface model, DSMs, we're computing canopy height for the whole state, and we're making these difference maps. So this is just all one big processing workflow. The final product is something like 4 terabytes of data. We did it on some fancy machines, but we estimate that if you were to try to do this yourself on just like a standard commodity cluster, it might take you about a year of compute time. So this is like non-trivial. And so there's some trickiness to doing this about how the data are organized in that AWS bucket. We also are dealing with coordinate systems. So we're actually backing out the datums and then solving for the datums and when we grid the data so that we're actually not mixing the signal. What we're seeing is actual change or other things, and we're not seeing coordinate system related errors. So that's also kind of cool. So this is in cartoon form. What this looks like is basically we go from San Diego Supercomputer Center to this bucket in Amazon. We pull out the data sets, and we're doing this in chunks, basically. Then, so we get the point clouds back. We rasterize them into, say, a DTM or a DSM, depending on what sort of part of the landscape or imaging change in. And then we compute the difference, right? And again, the difference maps are these red, blue things. So I'm going to show you now 2 images. This is the digital surface model of the whole state of Indiana computed. And so from back there where you're sitting, you may be a little hard to see to tell what you're seeing here. Again, remember red is erosion or downward motion, blue is upward motion. Turns out in the digital surface model, the biggest thing you see is changes in seasonal vegetation as a function of when the data were collected, right? So if you flew leaf off versus leaf on, you see that signal most significantly. There are other things in here, but they're anthropogenic or earth surface processes related, urban development. I'll show you some examples of those in more detail here in a second. So that's the digital surface model, right? Here's the digital terrain model. So this is the bare earth calculation. This one, you see the similar sorts of features like fluvial erosion, quarries, mining, urban development, but you also see all these stripes. See all the stripes in these data sets? That's swath misalignment largely in these data sets. It's the quality of the LiDAR data. There's like decimeter or more positional errors within the LiDAR data set that become quite apparent when you start differencing at the terrain mod, the DTM level. And so one of the take homes from this exercise is that the ability to detect change is only as good as the quality of the source data. Strictly vertical. Yep. Thanks. Somebody just asked if that was vertical or 3D. It's strictly vertical. So anyway, so that's an interesting outcome by itself. And we're not doing any kind of fancy swath realignment or any repositioning of aircraft trajectories or anything like that. We're just taking the data as it exists and doing this workflow. So that's another take home, is like, this is interesting, but there's also some polygons that are missing, and that's an artifact of what's in that Amazon bucket. Some of the data didn't get published, and so where we don't have data sets, you just see no data. So that's that. So next, I've got just 4 examples of zoomed in what this actually looks like in more detail. So of different types of change, basically, that we see. So the first is, this is like housing development outside of Indianapolis. So on the left in these next set of figures, you're going to see a toggle, which is basically the comparison of the two products, so DTMs or DSMs from the two time steps. And this was, just to remind you, the early data set here was collected between 2011 and 2013, and the later data set was collected, I think, 2018 to 2020. So it's roughly decadal change, but depending on where you are in the state, it's less than that oftentimes. And then the image on the right is the vertical difference map. So in this case, you can see that there's a bunch of new houses built, right? And so if you want to get fancy here, you calculate the volume of land or urban development or whatever, but that's what you see in this one. This is a limestone quarry near Louisville, Indiana. And here, obviously, large signal related to extraction of materials and moving materials around and stockpile volume change and all those kinds of very clear signals. Pretty large. You notice the scale bar there is 15 meters. So some of these piles have got really, really big. Let's see, what's the next one? Fluvial erosion. So I'm a geologist by training, so I like these next two examples. This is the Wabash River. So this is river meander. You can see that in general, you can see where the deposition's happening. This is a good example. If you're looking at the image on the right, you can see that there's a swath down the middle that looks higher, that looks like it's lower. And that's one of these internal errors within the data sets. It's a swath misalignment. And you can tell them because they have very distinct boundaries, very linear distinct boundaries that are on the flight line edges, essentially. So that's not real signal, that's something inside about the data sets. Here's an example at Indiana Dunes National Park along the shoreline of Lake Michigan, where you're seeing pretty significant coastal erosion, or lake, I guess, coast erosion. And this is, again, a place where this is actually a known issue. This is a PBS NewsHour special about this specific site and about erosion on the shore of Lake Michigan that was just out 2 weeks ago or so, talking about this problem. And it turns out you can see it quite clearly in the LiDAR. This erosional process is happening. So you could quantify that if you were diving into these data. So wrapping up, we did this in Indiana, right? And I think I hopefully made the case that this is non-trivial, but it's actually it's very exciting. It's very cool, the fact that we can start looking at these sort of decadal, or maybe better, depending on the repeat frequency of these types of collections. So what we did is we went into the USGS 3DEP catalog as well as the US Interagency Elevation Inventory, which in theory, some intersection of those two things should represent most of the publicly available high resolution topography in the United States. Any place on this map that's shown in black, there's at least a pair of data sets. So it's basically a third of the lower 48 right now have overlapping data. And so in theory, you could go through and do this exercise over roughly a third of the United States right now. We haven't done this. We just did it for the state of Indiana at the moment, just to demonstrate the process. But that is get you thinking about what we can start doing with these data sets beyond just using them as single epics, but they're repeat, and they have a lot of really interesting information within them. And it's non-trivial to produce the difference maps, but then making sense of those difference maps is also potentially an interesting exercise, right? When you've got change at 1 meter resolution, raster resolution, how do you make sense of that? This is a place like where machine learning or AI become really interesting. Can you programmatically walk that difference map and quantify what each pixel represents, right? Is it vegetation change? Is it land use change? Is it error? So I think I just already said basically the take homes here, but the automated workflows leverage remote resources. So this is a really cool and powerful thing in this world where we live in, where data are now being available in these cloud-based buckets, and we can start reaching into them and processing them. That's really exciting. And this becomes increasingly feasible as programs like 3DEP grow and collect more data, and that data becomes accessible, right? So you can imagine if we start having a 5-year repeat cycle of the whole US or something, you can start looking at land use change at sort of in that 2.5 dimensional sort of way. And then just a little bit of pitch that like we did this based on things we've built inside of OpenTopography. And so we're super interested in partnerships and working with other groups who are potentially interested in these kinds of exploratory exercises and want to leverage some of the stuff that we've been doing thanks to our funding from the National Science Foundation. We really think OpenTopography could continue to grow as a platform. It's a very collaborative space for people to manage these kinds of data and really do interesting things with them. So that's it. I'll be around till Thursday evening if people want to chat. So thank you very much.
So in NISJIC form, we have the microphone rule in effect. So in order to ask a question or comment, please come to one of these mics. We only have a couple minutes left, but also Jamie will be keeping track of those that have a comment or question in our Zoom presence there too. So please come to these microphone stands for a couple quick questions. No one's here at the microphone just yet, but yep. And then we'll go right to Jamie.
Do you have people trying to get bigger data sets than you can manage, asking you to difference huge swaths? What do you do about that?
Well, so right now, anything that's hosted inside of OpenTopography, you can run these kinds of on-demand process. You can do this kind of differencing on sort of small cases. So like basically like make a selection and we have the tools to do it. When you get up to this like statewide scale, we did it on the back end basically, because you can't do that through a web browser. This is really the only feasible when the data are either inside of our system or in something like that Amazon web bucket that the USGS is producing. And so I think this is exciting. And like, if there are other states who are sitting on data sets that are different than what's already inside that 3DEP bucket, interesting to talk about publishing those data sets into some environment that's either natively OpenTopography or uses the 3DEP data bucket kind of model as to replicate it. So especially the Amazon public data set program, they're hosting that data and they're providing egress for free. Right, that's pretty cool, right? And they're definitely, the Amazon public data set team, I think, is interested in more partnerships around interesting types of geospatial data. I can put you in contact with the people at Amazon if you want to if you want to explore this. But I think it's a great way to start managing these large geospatial data sets in a way that potentially has very low cost for the states.
All right, we'll go to Jamie for one, and then Megan is jumping up here. So Jamie, do you have a question or any comments from the chat that you'd like to convey?
Yes, thank you, Frank. Joanne Markert has a question. Joanne, are you comfortable coming off mute, or would you like me to read your question?
Well, no, I can come off of mute. Thank you. I was just kind of wondering about typical charges for this type of service, or kind of how does that work? And we have an awful lot of, we have some data in Washington that isn't in 3DEP. So how could we work with that?
Yeah, so for data sets that are not in 3DEP, we would basically take the model which you've taken with Land Information New Zealand, which is essentially you would provide the data to OpenTopography, we would host it on our resources, and we have a cost model that essentially covers our data storage, the on-demand compute costs, the egress, and we essentially end up providing your user support as well, because people, when they ask questions about data, they email us, they don't email you anymore when the data is in OpenTopography. And so that's the model, and I'd be happy to talk more about it, but it's not free, but it's a lot cheaper than recreating something like OpenTopography yourself at the state level.
Hi, Megan Compton, State of Indiana. Thank you for doing this. We love talking about our partnership with OpenTopo, and thank you to Phil, who I'm sure is on the phone, who helps keep us in line. I guess I would like for you to maybe expand a little bit, just in trying to figure out how we're going to host the next set of imagery. And right now we're sort of, I shouldn't say sort of, we're literally out there shaking the can, right? Fundraising, passing the hat around to everybody to try and get our 2018 or 2017 up LiDAR hosted. I'd like to hear a little bit about the difference in how things changed for you in data hosting from the last data set in 2011 till the current data set.
Yeah, so the our challenge is that the National Science Foundation funded the production of Open Topography, but the National Science Foundation really wants to spend money on novel earth science research and education. They don't want to be funding a clearinghouse for the state's geospatial or frankly the USGS's data distribution. And so this is a tension that we've struggled with. And so the partnership with Indiana in 2011 is still a great model, but I appreciate that most states don't, that even tens of thousands of dollars is sometimes hard to come up with, which is sort of order of magnitude for hosting of these types of data sets, depending on how much data you actually have. Is it a statewide collector? Is it just a tiny polygon over some county or something, right? So costs go with size of data. And so we're open to like exploring creative models to make this happen. We've been trying not to charge the end user. That's another potential scenario, is you charge the end user for that access to the system. We're a not-for-profit enterprise with a very academic worldview. We just have had a lot of interest from people at the state level. And I think the Indiana partnership in early 2010s was a great example. We point to that one still as a really successful model. And so we'd just love to talk to people about how to make this work. Thanks.
Thanks again.